So our next topic is particle in a box. However, before we discuss particle in a box, let us make some general observations about the continuity property of wave function of the Schrödinger equation. So let us consider the time-independent Schrödinger equation. And it's a second order in space. And we write it in this form. Then we can make things a bit clearer. We can write it as 2m e minus v divided by h bar squared psi. Now for realistic physical situation, the potential function v of x will be a continuous function. So this will be a continuous function for realistic situations. But sometimes we may want to idealize our system in which the potential function may be discontinuous. So for example, a realistic situation might be that the potential energy changes like that, but we don't want to deal with the intricacies of, say, of this region, for example, and we might want to, as a first order or zeroth order, we might consider to be a step potential, and then the potential over in this region changes abruptly and discontinuously. So what happens when the potential changes discontinuously? So in that case, the right-hand side of the equation is changing discontinuously. So that means that in those situations, the second derivative of psi will also change discontinuously. But once we integrate that equation, psi prime itself, will be continuous. However, there is a particular case when this will not happen, and that's the case when the discontinuity in the potential is an infinite discontinuity. So if the discontinuity in the potential is infinite, so the discontinuity in this is infinite, then psi prime will also be discontinuous. However, psi itself will still be continuous. It may not be differentiable, but it's continuous. So now let us, after these observations, let us come and consider the one-dimensional box. So what is a particle in a box? So suppose that we have some box, and the box has some rigid walls. So these are perfectly rigid walls. And what we do is that we put a quantum particle inside. So of course, this particle won't be able to escape. So the particle in a box is a one-dimensional idealization of the situation. So, and it's represented by the following potential function. So for the particle in a box, we get a potential function which is 0 in a finite interval of the real line, say from minus L by 2 to plus L by 2. Otherwise, it's infinitely high. So let's draw this weird potential. So we have on the x-axis our space coordinate x, and on the y-axis we have the potential function. And then over here, suppose we have L by 2, and over here we have minus L by 2. So what happens is that the potential is 0 over here in between, and at L by 2 it suddenly jumps and it goes all the way to infinity. And similarly, at x equals to minus L by 2, it suddenly jumps and goes all the way to infinity. So this let us divide this into 3 regions. So let's call this region 1, and let's call this region 2, this region between the 2 infinite walls, and let's call this region 3. Now, what we're going to do is that we're going to show that the wave function psi is 0 in region 3 and region 1. To do that, what we're going to do that, we're going to start with a potential where instead of this being infinity, this is some very high, very large real number called V0. And it is V0 we're going to assume is greater than the total energy. And then we're going to solve the Schrdinger equation first in region 3. So in this situation, and then what we'll do is that after we have done that calculation, we're going to send V0 to infinity and regain the result that we're interested in. So what is the Schrdinger equation? So the Schrdinger equation is d squared psi dx squared minus, so we are interested in region 3, so let's give this a subscript 3, and then we have here 2m by h bar squared, and then we have V0 minus E times psi 3 is equal to 0. So this equation has a general solution, and you should be able to solve this. And the general solution, because the energy E is less than the potential energy V0, the solution will be exponentially decaying and exponentially increasing. So it'll be e to the power minus k1x plus b e to the power plus k1x. Here a and b are integration constants. And k1 is given by square root of 2m V0 minus E divided by h squared, and the whole thing within the square root. So this is, k1 is a positive number, and that's because V0 is greater than E. And then if you look at these two solutions, we see that this solution, the second part, as x becomes larger and larger, this becomes bigger and bigger. That means that if this were to be a physically sensible solution, we would find the particle far, far away from the center of the potential where we had bounded it. So that's not a physically sensible solution. So that means that for this to make sense, B must be identically 0. So therefore, we get the solution that the solution in region 3 is e to the power minus k1x. And now we take the limit where v goes to, okay, before we take that limit, let's just discuss, what does this solution look like? So as you remember, v is not infinite yet. So this solution in region 3 is an exponentially decaying solution, something like this. Which makes sense because, if the particle is within these two walls, but this energy is such that it cannot climb over the potential, but it can still kind of seep out and be found a little bit outside this box. Anyway, this is known as quantum tunneling, and we shall cover that in detail in a future class. So I don't want to get bogged down in that. So now what we're going to do is that we are going to, okay, let me just erase this. So then what we're going to do is we are going to take the limit in which V0 now goes to infinity. If V0 goes to infinity, we see that K1 goes to infinity. So K1 goes to infinity, and that means that e to the power minus K1x goes to 0. In other words, psi 3 goes to 0. So we have shown that in the limit where my potential, the wall of my box is infinitely rigid, there is no, the wave function in region 3 is 0. So similarly in region 1, we can show that the wave function there is also 0. So we can show that. So what we have shown is that psi 1 is equals to psi 3 is 0. So the interesting region is psi 2. So let us look at the region psi 2. So in psi 2, what's going to happen is that the potential energy in psi 2 is 0, right? So this equation becomes, what does it become? It becomes the equation where we have d squared psi 2 dx squared, and then we have plus 2m by h squared e of psi is 0, where e is a positive number. So this has the general solution of two oscillating function in space. So it's a prime e to the power I kx plus b prime e to the power minus I kx. So the difference between this solution and the previous solution is that here there was no I in the exponential, and here there are i's in the exponentials. All right. So here k is given by a positive number. It is 2me square root divided by h bar. Now, we know that because our potential difference is infinite, psi, the wave function, must be continuous. So at the boundary of this box, we can impose the continuity condition. So psi 2 at the boundary, at the left boundary, is going to be equal to psi 1 over there. But we know that psi 1 is 0. Similarly, psi 2 on the right boundary is given by psi 3 at that point, and we know that is also 0 there. So if you now plug in this equals to 0, this equals to 0 in this guy, what we find is the following set of equations. We find that a prime e to the power minus I kl by 2 plus b prime e to the power I kl by 2 is 0. And we also find that a prime e to the power I kl by 2 plus b prime e to the power minus I kl by 2 is equal to 0. We can now solve this equation for a prime and b prime, and so the way you do it is by you write this as a matrix equation, and the matrix equation, there's a matrix D, and that matrix is the matrix of the coefficients of the exponentials, e to the I kl by 2, e to the power I kl by 2, and here plus I kl by 2, e to the power minus I kl by 2, and this multiplying a prime, a column matrix of a prime and b prime, gives me 0, 0. So these two equations can be written as a matrix equation. And let me call this matrix, say, D, and let's call this matrix, say, X capital X, and this is a 0. So then this matrix is telling me the square matrix D acting on the capital X vector V is giving me a vector 0. So if this matrix, if I could invert this matrix, then I would have X equals to D inverse 0, which would be 0. So that would mean that A and B are 0. That's the solution. So the condition that there is a non-trivial solution to this equation boils down to the statement that this matrix is not invertible. In other words, the determinant of this matrix must be 0. So if we now work out what this is, we get e to the power minus I KL minus e to the power plus I KL is equal to 0. And we can solve this. The solution of this is sine of KL of 0, which means that the product of KL must be an integer multiple of pi, where n is some integer. So now we can solve for A prime and B prime now using this. So the equation, we can take one of those equations above and just plug in the value of KL, and then we have e to the power minus I n pi by 2 plus, say, b prime e to the power I n pi by 2 is 0. And so we can now multiply by one of these factors. And if we do this, then I get, say, a prime is equal to minus, say, b prime e to the power I n of pi. Now, what is e to the power I n of pi? That's nothing but minus 1 to the power n. So we get a prime is equal to minus 1 to the power n to the power 2 times b prime. So we get two sets of solutions. N is an integer, so if n is even, then we get psi 2 is given by a prime times e to the power I kx minus e to the power minus I kx. And of course, this means that this is 2I a prime sine of n pi over L times x. So this is one of the solution. And we can normalize this function. If we normalize this function, then this prefactor can be chosen to be this thing. So this is when n is even. So when n is odd, the solution that we get is psi 2 is a prime e to the power I kx plus e to the power minus I kx. So there's a plus sign here, and that means that it'll give you a cosine solution. And then if you normalize it, you get so these are the two kinds of solutions you get. However, notice that sine of, say, minus n pi x over L is equal to minus sine of n pi x over L. And there is no difference between these two solutions, the one with the minus and the one with the plus sign. And that's because our solutions to Schrdinger equation only matter up to a normalization. And so any multiplicative factor, any phase factor is just like, that is not going to matter. This is not going to change our normalization. So similarly, for the cosines, so cosine of minus n pi by L times x is going to be cosine of n pi over L times x. So without loss of generality, we can assume that n is either 0 or positive. The negative integers don't matter. However, if I choose n to be 0, then we see that psi 2 is identically 0. This is not a physical solution because this doesn't give me any probability about anything. So this is actually, so we have to exclude the n equals to 0 case. So the solution that we are looking for turns out to be psi of x is, there's two classes of solution, 2 over L square root sine of n pi over L of x, where n is 1, 3, 5, dot dot dot. So it's a n is a odd integer, odd positive integers, or 2L by half cosine of n pi L of x, where n is, say, 2, 4, 2, 4, 6, so on and so forth. Now, we haven't talked about what the energy of these states are. So to do that, let's go back to this condition. So this condition, we can, of course, go back to, and ask what K is. K is this expression over here. So if I plug that in, what I get is that the energy, well, I have to square that. If I square that equation, then I get that the energy is given by, is labeled by an integer, and it's given by h bar squared pi squared divided by 2m L squared n squared, where n is 1, 2, 3. It's a positive integer. So note a couple of things. Number one, that the psi, the wave functions, are of definite parity. And that is actually reflective of the fact that we chose our coordinate system in such a way that our potential was symmetric. If we were to draw the wave functions, so this is our x, and this is the wall, and this is the wall. Then the ground state is a cosine function, and it looks something like this. And the first excited state is going to be a sine function, which has odd parity. And then, as you go up in the energy, the next state will have even parity. It'll have basically three cosine bumps, and then the next step would be another function of odd parity, and so on and so forth. So this is observation number one. Observation number two, which is perhaps more important, is the fact that energy is quantized. So we see that the energy E depends on n squared, and it's inversely proportional to L squared. So if I make the box bigger and bigger, the difference between the energy level becomes smaller and smaller until this becomes a continuum. So this is quite an important observation. And what you'll see is that, like any quantum system which is bounded, so by bounded I mean in which the total energy is less than the potential energy, that it will be that the energy of that state is going to be quantized. We'll see this. And lastly, and of course, actually it's also very important, is that classically, ground state energy can be 0, But here we see that the ground state here is not zero. The energy of the ground state when the integer n is 1 is given by h squared pi squared divided by 2ml squared. And this is a illustration of what is known as vacuum energy, that in quantum mechanics, the vacuum has an energy, and this has very far-reaching and deep ramifications in physics.